So we were discussing capacitors yesterday. So we'll continue from where we left off. We saw the first three derivations. We had three equations. First one was capacitance. You know, Q is equal to CV is the basic equation for capacitance. Charge is given by capacitance times potential difference or potential. Q is equal to CV, where C is called the capacitance. And then we had second equation, capacitance of a parallel plate capacitor, epsilon 0 A by D. This is if the entire capacitor is filled with air, right? Filled with air. And if a medium is present, this is Ca. That means the capacitor plates are the space between capacitor plates is filled with air or vacuum. So Ca is what? Epsilon 0 A by D, where A is the area of the capacitor plate. And then C medium. What if you're filling that with the material? It is epsilon 0, epsilon r, A by D. We learned this yesterday. Epsilon 0, epsilon r, A by D. You can write down the formula. I'll send the formula sheet today. Right. Epsilon 0, epsilon r, A by D. Right. This is basic equation for capacitance. Second one is for a parallel plate capacitor with air as the medium. And this is for a non-air medium. It is epsilon 0, epsilon r, A by D, where epsilon r is equal to 80 for water. For water, it is 80. Okay. And then if a conducting slab is inserted, capacitance is what? I call it C dash. If a conducting slab is inserted, it is epsilon 0 A by D minus T, where T is the thickness of the slab that you introduced. Hi Sneha, good morning. Right. Then C double dash. This is a dielectric slab. You know what if it is a dielectric slab? Epsilon 0 A by D minus T plus T by epsilon R. We learned all these things yesterday, right? We did the derivation for these three as well. These three are important. Okay, these four derivations are important. Let me repeat. First equation is Q is equal to CV. Second equation is epsilon 0 A by D. That is for a parallel plate capacitor. And then for a if a medium is filled inside, it is epsilon 0 epsilon R A by D. And then if a conducting slab is inserted inside the capacitor, it becomes epsilon 0 A by D minus T, where T is the thickness of the slab. And then if you're introducing a dielectric slab means what? A dielectric is a medium that shows, or a material that shows some electrical effects, right? And you know, it has a dielectric constant. Okay, so it is epsilon 0 A by D minus T plus T by epsilon R. So these were the equations that we saw yesterday. And then there were few equations that I wrote in the end. First one was energy. Energy is half CV square. I'll do the derivation now. That's important. Half CV square or Q square by 2C or half QV. These are the equations for energy stored in a capacitor. And then energy density. Energy density means what? Energy density means the energy stored per unit volume. Energy stored per unit volume. Look at this. This is one capacitor, and this is one plate with the capacitor, second plate with the capacitor, right? And as you know, this is all positive, 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 while the second plate is full of negative charges, right? The electric field here is 0. The electric field here is 0. The electric field inside is sigma by epsilon 0, if you remember. Yesterday I told you. Right. There are two plates kept side by side, you know, and the region outside the plates. This is region number 1, it is field is 0. Region number 3, field is 0. Region number 2 is inside the plates. In between the plates, there the field is sigma by epsilon 0. And the field is from where to where? Positive, negative, positive, negative, positive, negative. And there was one question once, where is the energy stored? The energy is stored inside the electric field. The energy is stored in the electric field between the plates of the capacitor. So where is the energy stored? The energy is stored in the electric field. Remember, they asked once, where is the energy stored in a capacitor? The energy is stored in the electric field in between the plates of a capacitor. The energy is stored in the electric field in between the plates of a capacitor. Right. Anyway, the energy stored per volume. Energy stored per volume is, that means the energy is stored inside this volume, right? It is given by half epsilon 0 E square. This is called energy density, electrical energy density, right? Energy density or energy per volume. And then I told you there are two more equations which are very important. One is for common potential, C1 D1 plus C2 V2 by C1 plus C2. I'll explain this now. And then second one, delta U is equal to half into C1 C2 by C1 plus C2 into V1 minus V2 the whole square. And you know, If you check your previous papers, in school papers, you know, you can see this question being asked so many times. Okay, these are important equations. I'll tell you what it means. So this is equation for energy. Equation for energy density. Energy density means energy per volume. And common potential, energy loss. You can write this on a paper if you want. These are the formulae for this part. Okay, that's it. For capacitors, these are the formulae. Right. So what is common potential? I'll tell you about common potential. So hope this is okay. I'll come back and do this derivation and this one as well. These two derivations I'll come back after this. First I'll see this common potential and energy loss. What is common potential? What is energy loss? You must have done this in school. It is not explicitly given in textbook, but it is very important. Okay, chapter exercise has a question. What is common potential? I'll tell you. This is one capacitor, okay? The capacitor has a capacitance of C1 and it has a potential of V1. So it is charged to a potential V1. It is raised to a potential V1. And then there is another capacitor of capacitance C2. The potential is V2. And then you're going to connect these two through a wire. Right, you're going to connect them. What happens then? Just imagine, I'll tell you an analogy here. You know, we have a bucket of water. And we have a second bucket of water like this with a lesser amount of water, right? And then you're going to connect them through a pipe like this. What happens now? The levels are different. What happens now? Water flows from higher level to lower level till both attain a common level. And that is known as common level, right? So whenever there is a level difference, water flows from who is flowing? Is the level flowing? No. It is the water that is flowing. Water is flowing till what is equal, till the levels are equal. Similar way, if you take a hot body and a cold body in contact, keep a hot body and a cold body in contact, hot body and cold body, okay, ice with a flame or ice with a, boiled water, then what? You know, heat flows from hotter object to colder object till both attain a common temperature. So in this case, water flows from higher level to lower level till both attain a common level. In the case of hot body, cold body, heat flows from hotter body to colder body till both attain a common temperature. Similar way, if you connect them together, what happens? Charge flows from higher potential to lower potential till both attain a common potential. So the question is to find out common potential. What is the equation for it? C1 V1 plus C2 V2 by C1 plus C2. I'm not doing the numerical today because it is all direct substitution. They'll ask this question, they'll ask you to find out common potential. Everything will be given. C1 will be given, V1 will be there, C2, V2, everything will be. You just have to substitute C1 V1 plus C2 V2 by C1 plus C2. Say that once, please. You know, common potential is what? Whenever two capacitors at different potentials are connected together, charge flows from higher potential to lower potential till both attain a common potential. Common potential is given by C1 V1 plus C2 V2 by C1 plus C2. And you know, one thing is understood here. This positive is connected to positive, negative is connected to negative. What if the polarities are opposite? That means positive is connected to negative, negative is connected to positive. Opposite polarities are connected together. Such a question comes only in competitive examinations, JEE examinations. But one of you send me one question that involves this concept. Okay, since it is Birla, you have to expect it because it's a JEE, previous JEE question. What if the polarities are opposite? Here it is positive, positive connected together, negative, negative connected together, right? What if positive is connected to negative and negative is connected to positive? Opposite polarities are connected together. You just change the sign to minus. C1 V1 minus C2 V2 divided by C1 plus C2. Yes, Maharshi, that's right. C1 V1 minus C2 V2 divided by I've told you once in class during the first term divisions. C1 V1 minus C2 V2 divided by C1 plus C2. And while doing this, some amount of energy is lost. How much of energy is lost? The energy lost is called delta U. The equation is half C1 C2 by C1 plus C2 into V1 minus V2 the whole square. Look at this. What is this? While connecting this, charge is flowing through the wire. Charge is flowing through the wire. No, current is flowing through the wire. So it gets heated up. I square RT, Joule's law heating, class 10 physics, I square RT. Joule's law heating, I square RT. So the wire gets heated up. The wire gets heated up and you are losing energy. How much of energy is lost? This is the equation, half C1 C2 by C1 plus C2 into U1 minus V2 the whole square. Trust me, they won't ask you to prove this. You can prove this, but that was removed 6 or 7 years back. Okay, the proof is not there. If they ask, it's going to be a numerical. Don't worry, either of these will be asked. Okay? We just have to learn the equation C1 V1 plus or minus C2 V2 by C1 plus C2. Why plus or minus? Plates of same polarity plus plates of opposite polarity minus. Okay? And then what is the energy loss while doing this? It is half into C1 C2 by C1 plus C2 into V1 minus V2 to the whole square. Very, very important questions for boards as well. You just have to learn these equations. Did you understand this? So we have an equation for energy. How do you find the equation for energy? This derivation is very, very important. I'll do this. We have a capacitor connected to a cell like this. Okay. Now what happens when you connect the capacitor to the cell? You may feel like I'm rushing, but we have no option. Okay, I need to finish this in 2 hours. Okay, kindly cooperate. If you have any confusions, I can help you afterwards. Okay, right. I don't want to waste your time. Right. So this is a capacitor. The capacitor is connected to a cell now, and cell's polarity. So what happens now? What happens now? The capacitor starts getting charged. Now, how is it getting charged? Tell me, what is the mechanism of charging? This is positive, right? Positive has the capacity for attracting negative electrons, right? So electrons are one by one taken from the first plate. Look at that. First plate is connected to positive. So this positive terminal will take electrons one by one. So it gets positive, 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 positive like that. At the same time, negative will release electrons. They will come over here. That is how the capacitor gets charged. Understood? See, I was saying, how the capacitor is getting charged here, no? The capacitor is connected to a cell. The moment you connect it, it starts getting charged. How is the charging done? I told you the positive plate, the positive terminal is connected to the first plate, while the negative terminal is connected to second plate. Now what happens? This positive plate will attract electrons one by one. When electron is lost, it is like losing negative. Losing negative is equal to gaining positive. So it's positive, 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 positive. At the same time, electrons are released one by one. So negative, 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 negative. So one side is plus, the other side is minus. The capacitor is charged. Yesterday I told you the definition for potential. If you remember, W by Q. Work done per charge is called potential. Work done per charge is potential. So cross multiply. What is work done then? Q into V. Okay. So I'm going to find out the small work done. Small work done can be written as V into dQ. Why do I find the small work done? Because this process is a very slow process. It happens over a time. Am I correct? It's a time dependent function. Am I correct? The charge is being released, the charges are being released, and the capacitor attains its maximum charge over a long time. Am I correct? It's a time dependent process. It depends on time. It doesn't happen spontaneously. Right? It takes time for the charge to get to maximum value. Understood? So since it is a slow process, it happens very slowly. I'll take very small work done for a very small charge. Understood? See, work done is charge into potential. So small work done for a small distribution of charge. Small charging is given by V into dQ. That is what? This V is equal to Q by C. Yesterday we learned the definition of capacitance. So dW is equal to Q by C into dQ. Now you know what to do. If you know the small work done, you can find the total work done by integrating this. Integrating Q by C into dQ. Right? Since we know the small work done, we just have to integrate. Right? From where to where? Initially the capacitor had 0 charge. Finally the capacitor has maximum charge, which I call it capital letter Q. Okay, so integration should be done from 0 to Q. Tell me what you got. 1 by C is constant. I can take it outside. What is integral of Q dQ? Integral of Q dQ means Q raised to 1. Q raised to 1's integration is Q square by 2. Q raised to 1 plus 1 plus 1 plus 1 by 1 plus 1. Q raised to 1 plus 1 by 1 plus 1. So it is Q square by 2. So I put it here. This is Q square by 2 from 0 to capital letter Q. Tell me what you get. The lower limit is not to be given. It is 0. So there is no point in giving lower limit. Just give the upper limit. Okay. In place of Q, you put Q. So this is Q square over 2C. This is the work done to charge the capacitor. And by putting Q is equal to CV, you can get another expression, half CV square or half QV. There are 3 equations for energy. This is work done. This work done will henceforth be called U, potential energy. Energy stored in the capacitor. So I'll quickly do this one more time. I'll find the small work done for charging through with a small charge dq. Small work done is V into small dq, and then dw is equal to q by c into dq, and then w is integral q by c into dq. That's it. So easy. You are charging from where? Zero charge. Initially, capacitor had no charge, and then finally it has full charge, capital letter Q. So once you've done the integration, which is q square by 2, you give the limits. First, give the upper limit. I don't care to give this lower limit because it's 0 anyway. So you just give the upper limit, it is q square by 2c. And if you modify this equation, you'll get half cv square, another equation, half qv, a third equation. This is the work done to store. Work done to charge the capacitor, which is stored as energy inside the capacitor. And there can be one question: what is the total energy supplied by the battery? Total energy supplied by the battery will be QV or CV square or Q square by C. Total energy supplied by the battery. Look at that. This is Q square by 2C. This is half CV square. This is half QV. This is the energy stored in the capacitor, no? Energy stored in the capacitor. This is the energy supplied by the capacitor. Energy supplied by the capacitor. Energy supplied by the capacitor. Now, this is actually QV, but here it is only half QV, half of it. This is CV square, but this is half CV square. And this is Q square by C. This is Q square by 2C, only half of it. Where has the rest half gone? The rest half is lost as heat on the wire, connection wire. Okay, just in case, it's an extreme level question, but they won't ask. It's a community examination question. Find the ratio of energy stored to the energy supplied by the battery. Energy stored is half of energy supplied. Where is the rest half gone? The rest half is lost as heat on the connection wire. I'm repeating. Energy stored is Q square by 2C or half CV square or half QV, while energy supplied by the battery, energy supplied will be what? Will be double that value, double this value. Q square by 2C is double value Q square by C. Half CV square is double value CV square. Half QV is double value QV. So out of this, half is gone. Half is gone where? Right. Another option is on the wire, connection wire. Did you understand this? Okay, energy density. What is energy density? Energy density is actually energy by volume, right? Energy by volume. Energy density is energy by volume. Energy is half CV square over volume is what? Look at this. I have two plates. And volume. How do you find the volume? Area of this plate into distance between the plates. Or just look to the left. You see a wall, right? Look to the right, you see another wall, right? Okay, you're sitting in a room, right? I presume that you're sitting in a room. So on the left side, you got one wall. On the right side, you got another wall, right? And you got to find the space, volume in the volume of the room. How do you find the volume between the walls? Area of one wall into distance between the walls. Am I correct? Just imagine these to be the plates of capacitor. And then what? Area of one plate into distance between the plates. Look at this. This is area of one plate into distance between the plates will give you what? That will give you the volume, right? So I can put area into distance, right? And tell me what you got. This is half into capacitance value. I can put epsilon 0 A by D, right? Into voltage. Yesterday I told you voltage is what? E into D. Voltage is E into D. E into D. Because yesterday we had one equation: electric field is equal to voltage by distance. Do you remember? Potential gradient E is equal to V by D. Cross multiply, this E into D. The whole square over A into D. So let us simplify this. What do we get now? What do we get now? This is half into epsilon 0 A by D into, this is E square, D square divided by A into D. So let us cut these. A and A are cut, then D and D are cut, then D and D are cut. You are left with half epsilon 0 E square. So the final answer is half epsilon 0 E square. Did you understand? Okay, so there can be another question. Write the principle of a parallel plate capacitor. Check the notes, it is there. Okay, we have a conductor and there is a limit up to which you can give charges. And if you give more than that, those charges will leak to the surroundings. So how do you increase the capacitance? The best way is to bring another plate close to this. What happens now? Electrons will be pulled to the side. Electrons, negative, 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 right? The farther side will be positive, because that side has lost electrons, no? So it's all positive on the right side. And then if you connect this to the ground, those charges will lead to the ground. So those charges are gone. Now only negative charges are left, which means what? Positive potential was there. This was a huge positive potential that's being reduced by this negative potential. When potential reduces, denominator decreases, means capacitance increases. Hope you understood. Okay. All right. So we'll see some questions now. These are important questions. First one, I'll tell you, we have done this 2-3 times. Anyway, I'm doing it one more time. Look at this, the first one. Now, this is a capacitor arrangement. Okay, capacitor arrangement. And they'll give it like this. What sort of a combination is this? If you see something like this, this is parallel combination. Parallel combination, because these lines are being short circuited. This is parallel combination. It's a standard question. So the moment you see this, you can, and in school, you know, they might give one more capacitor here and one more capacitor here or something. Don't worry about it. Take it as a standalone case and then replace that with a parallel combination. What is parallel combination? Forget about this part. Do this part now. Right. What is parallel combination? Why is it parallel combination? Why is it parallel combination? How come it is parallel combination? You don't have to know actually. But even then I'll tell you, look at this. This point is short circuited to this point. So this point and this point are the same. They are the same potential. Okay, that's called short circuiting. Short circuiting, you know, you just walk along this path. Do you encounter anyone? No. Do you see anyone? No. No. Until you reach here, you don't see anyone. Which means what? This point and this point are the same potential. Similarly, so if this is A, I can call this nu A. So I can wipe the extension off. I don't want it anymore. Similarly, if this point is B, I can walk along this. I'll come over here and this is also B. Right. So this is my nu A, this is my nu B. How many capacitors are there between A and B? A to B one part, A to B second part, A to B third part. There are 3 parts. And if you find it really complex, you know, you can just learn it as it's a parallel combination. What is effective for parallel combination? The effective is all are C's. C plus C plus C. That makes it 3C. The answer is 3C. That is question number 1. Question number 2. You know, you have done this in resistors. Hope you remember. You will see the same configuration with 2 capacitors here. Look at that. Look at that. Here and here. Now, there is a difference between these two. What is the difference? What is the difference between these two? Here you have no capacitor here either, right? But here we have a capacitor here and here, right? There are 2 capacitors here, right? It's a Wheatstone's bridge. This is actually a Wheatstone's bridge. Look at this. If I draw a line through the middle, right? These 2 are on the left side. These 2 are on the right side. You tilt your head and see for yourself. Tilt your head. Or turn your notebook. That's better, right? If you have drawn this, right? And these are on the left side. These are on the right side. So you should write like this is left to top. This is left to bottom. This is right to top. This is right to bottom. Central arm can be removed then, right? Balanced Wheatstone's bridge. So this is one path, take them in series. This is another path, take them in series, then take them in parallel. Okay. I'll repeat this. We had a capacitor here. There is a difference between these two. Okay. But be very careful while doing this question. See if you have any capacitor here. If you don't have any capacitor here or here, that will be a parallel combination. You know, this one, this one, this one. They are in parallel combination because those points are short circuited. So C plus C plus C would do. That is 3C. In parallel combination, it is 3C. But on the other hand, if it is having capacitor here, it is like a Wheatstone's bridge. It's a standard question. So you draw a line through the middle, and then what? These are on the right side. This and this are on the right side, the right hand side, and these guys are on the left hand side. So this is right to top. This is right to bottom. This is left to top. This is left to bottom. This is central arm, which can be removed. Central arm is removed means what? These are in series. Now these 2 capacitors are in series. They can be taken in parallel combination. Did you understand this? This was given by your teacher, but it's again a removed portion, but removed question anyway. I'll do that. Just see this. We have n number of droplets. We have n number of droplets. They are combined to form a big drop. N droplets are combined to form a big drop. N droplets are combined to form a big drop. What happens to capacitance? Okay, or show that capacitance is this. I'm going to prove this. Capacitance of big drop will be equal to n raised to 1 by 3 into capacitance of small drop. Okay, so just in case they ask, the question is this. N droplets, small droplets, n of them are joined together to form a big drop. Okay, so if capacitance of big drop is Cbd and that of small drop is Csd, they are related by this equation. Show that this is correct. I'll do this. Now, before doing that, let me ask you, what is being conserved here? Look at this. You have neither added water nor removed water, right? Which means volume of water. Volume of water is what? N into 4 by 3 pi r cube will be equal to 4 by 3 pi capital letter R cube. I'll repeat. Volume of a single drop is what? Droplets are spherical in shape. Am I correct? For a sphere, the volume is 4 by 3 pi r cube. For one drop, it is 4 by 3 pi r cube. N droplets, it is n into 4 by 3 pi r cube. Yes, Hannah, right? Yes, Hannah. 4 by 3 pi r cube. On the right side, there is only one drop, but the volume is 4 by 3 pi capital letter R cube because there the radius is capital letter R. Okay, so I can get this 4 by 3 cut, pi cut, and what do we get? N R cube is equal to R cube, or R will be equal to n raised to 1 by 3 into small r. Capital letter R is equal to what? Capital letter R is equal to, I take the cube root. Capital letter R is equal to n raised to 1 by 3 into small r. You could even learn this equation by heart. You don't have to know this. Okay, do this. So just write R is equal to n raised to 1 by 3 into small r. And I'll write the capacitance of a sphere. Capacitance of a small drop is capacitance of big drop. I'm writing capacitance of big drop is equal to 4 pi epsilon 0 r. Because for a capacitance of a sphere, the equation is 4 pi epsilon 0 r. This is what I said. It's not there in the syllabus anymore, but I saw in one of the worksheets that was sent to me. Okay, from your school. Some of you send me one worksheet. Right, had this question. You know, capacitance of big drop is equal to 4 pi epsilon 0 times r. 4 pi epsilon 0 times r. Using this, you can find the capacitance of Earth. Earth is like a sphere, no? So 4 pi epsilon 0 value you can put. Radius of Earth is 6,400 kilometers. And if you calculate it, you are going to get 711 microfarad. That is capacitance of Earth. Forget about it, you won't need it. Okay, so I'm writing it 4 pi epsilon 0 into what is capital letter R? N raised to 1 by 3 into small letter r. If you take these together, what is that? N raised to 1 by 3 into 4 pi epsilon 0, small r is what? 4 pi epsilon 0, capital letter R is C big drop. 4 pi epsilon 0, small r is then what? C small drop. So Cbd is equal to n raised to 1 by 3 into Csd. Did you understand this? Okay, right. So we'll go to the next section. Series and parallel cases. Look at this. You know, we have done this, even then I'm doing it one more time. Look at this. Capacitor is taken and the left half is filled with one material. Right half is filled with another material. Okay. Left half is filled with one material of dielectric constant K1. Right half is filled with another material of dielectric constant K2. And another case is there. The top half is filled with one material K1. Bottom half is filled with another material K2. Right. So there are two cases. Yeah, no issues, Sariba. Right. So this is what? Now this is a capacitor whose left side is filled with one material, right side is filled with another material. For this one, top half is filled with one material and bottom half is filled with another material. Right. And this is to be seen as a series combination. This guy is to be seen as a series combination. Because left right should be what? Series combination. And top bottom should be seen what? Parallel combination. And in order to complicate things, in your school, last time when it was asked, they kept it horizontally. And you would think that it is what? They would keep it like this. Okay. And you would think that it is top and bottom. No. You have to keep it in the vertical direction. Because it should be, plate should come, as you walk from left to right, you should meet the plate. That is the condition. You should hold the capacitor in that orientation. Did you understand? See, this is a series combination when the space between the plates is filled with different materials, you know, if left, right are filled with materials, left, right, if it is left, right, that means left part with one material, right part with another material, this is to be seen as a series combination. While it is top half and bottom half, it should be seen as a parallel combination. But you know, when it was asked in your school, they held it in horizontal orientation so that you won't get marks. Understood? So you would think that this is what? This is top and bottom, but that is wrong. Because as you walk, you don't meet the plate. Here, you know, you are walking. This is you, right? You're walking. And as you're walking, you are meeting the plate. And this is you. You're walking. And as you walk, you meet the plate. Understood? So if it is held like this, you should hold it in the vertical orientation. The plate should be left and right. Understood? And this is series combination. Second one is parallel combination. I'll write down the equations for this. Then we will do the questions. Okay, right. Be very careful here. Yeah, right. So first half. How do you find the capacitance of this? Capacitance is given by epsilon 0 K1 A by D by 2. K1 A by D by 2. Why D by 2? For the first half, look at the spacing, it is D by 2. Second half, look at the spacing, it is D by 2. Left half with one material D by 2. Right half with another material D by 2. D by 2, D by 2. Left half, right half. It is what? So for first part I am writing epsilon 0, epsilon R, A by D. That was my equation. Do you remember? If you fill with one material, the equation is epsilon 0, epsilon R, A by D. So here epsilon R is given as K1. So it is epsilon 0, K1, A by D by 2. Why D by 2? I told you the distance is D by 2. Take it out in numerator. 2 epsilon 0, K1, A by D. Similar way, C2. This is C1. C2, second capacitor. It is what? Epsilon 0, K2, A by D by 2. It is 2 epsilon 0, K2, A by D. Correct? So, you know, how do you find the effective? These are in series combination. I'll tell you an easy method. You know, I'll take these together as X. Okay, so that it appears to be K1X. Why? Otherwise, you'll have to carry the whole term throughout. Understood? It will look really complex. So instead, 2 epsilon 0 A by D, if you take it as a single term X, it will be easy for you. Here also, 2 epsilon 0 A by D can be taken as X. So that makes it very short. K1X and K2X. Now what? What is the effective for C12? C12. C12 means the effective of 1 and 2. The effective of 1 and 2. What is that? It's a series combination. Series combination equation is C1 C2 by C1 plus C2. If you remember, series combination. Parallel combination is direct addition C1 plus C2. Series combination is C1 C2 by, tell me Harshita, C1 C2 by C1 plus C2. That is what? K1X C1 into K2X by K1X plus K2X. So what do we get now? I'll take what? This is K1, K2 into X square by K1 plus K2 into X. 1X gets cancelled here. Final answer is K1, K2 by K1 plus K2 into, what do we call X? X is there, no? X was 2 epsilon 0 A by D. Did you understand this? The first one? Parallel combination is top and bottom, no? Top and bottom. So the top half gets only half the area. Look at that, top half gets only half the area. So C1 will be what? Epsilon 0 K1 A by 2 by D. Why? Because look at this, half the area goes with the top half. Right? Bottom capacitor gets half the area. When I say area, I mean area of one plate. Area of one plate. Okay, it is half the area goes with the top capacitor, half the area goes with bottom capacitor. So that makes it what? Epsilon 0 K1 A by 2D. Right, this 2 goes to denominator. Similar way, C2 is also say epsilon 0 K2 A by 2D. Easy to find out C12. It's parallel combination, no? C1 plus C2. Parallel combination is C1 plus C2. So epsilon 0 K1A by 2D plus epsilon 0 K2A by 2D. If I take epsilon 0 A by 2D common, inside you got K1 plus K2. Understood? This is a previous IIT question and it is supposed to be the toughest question ever asked from this section. It was asked in ideal school last year, maybe asked in your school as well. We have done this question in class, in our regular discussions and in our first term revisions also. We did this. If you're drawn, I'll do this. Look at this. What is the first thing to do? As you walk, do you meet the plate? As you walk, do you meet the plate? No. The plate is where? Plate is on top and at the bottom, no? You have to keep it in the vertical orientation. So I'm keeping it, first of all, I'm keeping it in the vertical orientation. Look at that. I'm turning it through 90 degree. You turn your notebook through 90 degree. You turn your notebook through 90 degree. This is K1, this is K2, this is K3. It would look like this. Am I correct? K1, K2, K3. Right. K1, K2, K3. Yes, that's right. So you turn it through 90 degree. The configuration will look like this. K1 on top. Look at that. Oh, K2 on top. Okay, fine. K2 on top. Doesn't matter much. Even then. K2 on top. K1 there. Then K3 on the right side. So the question is, what is the effective dielectric constant? K1, K2, K3. If I write effective as K, get a relation between K, K1, K2, K3. Okay, right. I'll repeat. What is the question? We have a capacitor with combination, and then what? If I replace the whole with a capacitor of K, dielectric constant K, you get an expression for K in terms of K1, K2, K3. Just see what I'm doing now. Look at this. What about K1? What is the capacitance for K1? I'm writing the capacitance for K1. C1, I'm writing it as C1. Epsilon 0, K1. What is the area for this guy? Look at this. What is the area? It gets only half the plate. Look at this. It gets only half the plate. Am I correct? It gets only half the plate. So, yes, area is A by 2. What about the distance here? Distance also, right, it is D by 2. See the distance. The total spacing is D. Half the spacing will be D by 2. So, 2 and 2 are cut. You get what? Epsilon 0 K1 A by D. All right. Similar way, I can write C2. I don't have to do it. It is repetition with K2 in place of K1. K1 and K2 are identical, huh? Right. So I take one plate here. This is half the plate again. So it is what? I'll write down the same thing. Epsilon 0 K2 A by 2 by D by 2. Right. 2 and 2 are cut. You get what? Epsilon 0 K2 A by D. Now what sort of a combination are they in? They are in what combination? Top half, bottom half is what? It's parallel combination. Look at that. Top half, bottom half. They are in parallel combination. Then you can take it with K3. So these are in parallel combination. How do we take in parallel combination? C1, 2. I am taking C1, 2. It is C1 plus C2. C1 plus C2. So I am taking them together. It is epsilon 0 K1A by D plus epsilon 0 K2A by D. Right. So that is epsilon 0 A by D. If I take common, inside I got K1 plus K2. So I am halfway through now. Now this is C1, 2, between 1 and 2. What about C3, capacitance of 3? I'll do that somewhere here. I don't have space. Okay, I'll do that here. Right, C3. C3 is what? Epsilon 0 K3 A by D by 2. Look at that. For the third capacitance, epsilon 0 K3 is the dielectric constant. What about the area? It gets full area. Look at that, full area. Right. That guy gets full area, entire area of the plate. So it is A. But the distance is what? Distance is D by 2. So epsilon 0 K3 A by D by 2. Common sense. Then take it in numerator. You get what? 2 epsilon 0 K3A by D. 2 epsilon 0 K3A by D. Understood? This is C3. C3. So you got C1, 2. You got C3. They are in what combination? They are in what combination? Series combination. Right. So you should take what? C12 into C3 by C12 plus C3. So did you understand this much? I'll do the rest. So I've taken what? I've taken epsilon 0 A by D as X for simplicity. Here also epsilon 0 A by D as X. So 2K3X. Did you understand? Tell me if you're finished writing this. All right, Adiba? Faiz? Isa? Thank you, Jovita. Right, Habiba. Right. Then, okay. So I have done C12, I have done C3. Now you can find C123. Now C123. C123 means C12 into C3 by C12 plus C3. Right. C123 means the whole capacitance. No? C123. Whole capacitance. C12 into C3 by C12 plus C3. Because C1, C2 by C1 plus C2, right? So I'm putting the value. What is this? C12, C12, where is C12? Ah, this is C12, right? Okay, K1 plus K2 into X into, what is C3? 2K3 into X divided by, tell me what? K1 plus K2 into X plus 2K3X, right? So what have I done now? I've just taken C12 into C3 by C12 plus C3. That's again common sense. No physics, right? No hardcore concepts. It's like what? It's like these are in series combination side by side. C1, C2 by C1 plus C2. So C12 into C3 by C12 plus C3. C12 I put the value, C3 I put the value, C12 I put the value, C3 I put the value. Right. Now what? I can take the common terms there. So let us write it one more time. I am rearranging it. 2 into K1 plus K2 into K3, K1 plus K2 into K3 into X square divided by, I take X common on denominator, K1 plus K2 into plus 2K3 into X. I get 1X cut. And this is effective, no? This is effective. What is C123? I am replacing with an effective of epsilon 0 Ka by d. Epsilon 0 Ka by d. This is effective, no? Effective means what? I am replacing the whole capacitance with a single effective of K. The whole thing with a single effective. In that case, it is epsilon 0 Ka by d. Right. So epsilon 0 Ka by d is equal to 2 into K1 plus K2 into K3 by K1 plus K2 plus 2K3 into X is there. What was X? We called epsilon 0 A by d as X. So epsilon 0, A, D, D, cut. So final answer is A is equal to 2 into K1 plus K2 into K3 by K1 plus K2 plus 2K3. Did you understand this? We did this question class. If you want the video clip, I can send you. Video solution I can send you if you want. But try this at home. We can do this. So easy. Same concept. Only thing is that, you know, this should be one capacitor. This should be another capacitor. They should be in series. And that guy should be in parallel with this one. Understood? Say something, please. I'm asking all of you. Tell me. So we have a parallel plate capacitor and there is an aluminium foil introduced in between the plates. Right in the middle. What happens to capacitance when the aluminium foil is introduced? There are two cases. One case, you know, you will connect these through a wire, right? The first plate is aluminium foil by a wire. What happens in this case? What happens without this? So we'll do without the wire first. Now, first case is what? You know, you're introducing the aluminium foil. This is an aluminium foil. It's a previous board question. It was there in Birla paper also. It's important, right? Okay, you're introducing an aluminium foil inside. You will calculate the capacitance, new capacitance, no? Original capacitance was epsilon 0 A by D, right? Epsilon 0 A by D. Now, this part is C1, this part is C2. I'll take them as two capacitances with D by 2 spacing, D by 2 spacing. What is the capacitance for the first one? Epsilon 0 A by D by 2. Epsilon 0 A by D by 2. This goes to numerator, 2 epsilon 0 A by D, right? Similarly, what is C2? C2 is what? Second part. Second part is what? That is repetition of the same thing, no? Epsilon 0 A by D by 2, 2 epsilon 0 A by D. I can call this 2 epsilon 0 A by D by the name X. This is also X. They are in series combination. So what is the effective? What is the effective C dash I would call? I'd call it C dash. X into X by X plus X, which is X square by 2X. That is X by 2. What did we call X? X was 2 epsilon 0 A by D by 2. 2 and 2 are cut. Epsilon 0 A by D. What is epsilon 0 A by D? That is equal to C. That means capacitance remains unchanged. I'll repeat the case one more time. You know, we have a parallel plate capacitor and we're going to introduce what? An aluminium foil, a thin aluminium foil inside the plates, in between the plates. And this spacing is D by 2. This spacing is also D by 2. Then what? I'm finding this capacitance first. C1 is equal to epsilon 0 A by D by 2. This spacing is D by 2. 2 goes numerator to epsilon 0 A by D. I call this by the name X, 2 epsilon 0 A by D by X. Then second capacitance is identical to that of the first one. So epsilon 0 A by D by 2 again. That makes it 2 epsilon 0 A by D, right? That is equal to X again, right? Same thing, no? So effective is these are in series combination. So C1, C2 by C1 plus C2, X into X by X plus X. That is X square by 2X. 1X is cancelled. You get X by 2. X was what? 2 epsilon 0 A by D. 2 epsilon 0 A by D by 2. 2 and 2 are cut. You get epsilon 0 A by D. What is epsilon 0 A by D? Is C, old capacitance. That means new capacitance is same as old capacitance. What if case number 2? What if these are connected by a wire? One of the plates is connected to the aluminium foil. What happens is these two will come to same potential because charge will flow from this plate to this aluminium potential. So this part of the capacitor will be spoiled. That will be spoiled. Okay. Did you understand? This is C dash, right? Okay. Case number 2 is you are connecting these two, one of the plates to the aluminium foil by a wire. What happens then? This plate and this aluminium foil will be at the same potential because charge flows from this plate to the aluminium foil. Higher potential to lower potential. The question is, you are introducing an aluminium foil. Case 1, what is the new capacitance? Case 2, what is the new capacitance if one plate is connected to the foil? Did you understand, Shona? This part is what? What is the new capacitance if one plate is connected to the foil? So when you connect them using a wire, charge flows from higher potential to lower potential, no? So these will be at same potential. Same potential means they won't make a capacitance. So this part is the remaining capacitance. I can call it C double dash. What is the value of this? It is epsilon 0 A by D by 2. Take it out of the numerator, 2 epsilon 0 A by D. And these are together. This is 2 into. What is epsilon 0 A by D? It is C. So 2C. So capacitance becomes double the original value. Double the original value. Right. You know, draw the graph of Q and V. Draw the graph of Q and V and find the area under the graph. Slope of the graph. Now these 2 points are very important. Q is proportional to V. Do you remember? Tell me what? Q is proportional to V or Q is equal to CD. We learned this, right? And if you draw the graph with Q on y-axis and V on x-axis, as you can see, we are having what? Direct proportionality here. Direct proportionality, no? Direct proportionality. That means the graph will be a straight line. The graph will be a straight line. Okay. So Q and V are directly proportional to each other. So if you draw a graph of Q with V, it's going to be a what? It's going to be a straight line like this. And then I'm going to take 2 things here. Look at this. The first thing is the slope of the graph. How do you find the slope of the graph? Slope means tan theta. How do you find tan theta from the graph? You have to create a small triangle here, somewhere here on the line. Understood? Yeah, that's right, Maharshi. You know, you're finding the slope of the graph. Slope means tan theta. Tan theta is what? Opposite side. That is Q. Come over here, opposite side. It is Q. Divided by adjacent side. It is V. So Q by V. What is Q by V called? Capacitance. Q by V is called capacitance. Then second one, area under the graph. Area under the graph. What does area look like? The area looks like that of a triangle, right? Area is a triangle. What is the area of the triangle? Yes, half into base into height. Base is V. Half into base is V. Height is Q. So half QV. What is half QV? Energy stored. Energy stored. Okay. So just now that the slope of QV graph is capacitance and area under the graph is energy stored. Area under the graph is energy stored. Okay. Right. I'll repeat one more time. Q and V are related by the equation. Q is directly proportional to V, or Q is equal to a constant into V, C into V. Okay. And then if you draw the graph is a straight line. I take a small triangle somewhere here and then take slope. Slope of the graph is tan theta. Tan theta. Tan theta is opposite side, that is Q, by adjacent side, that is V. Q by V. Q by V is capacitance. Okay. And then area under the graph. Area under the graph is that of a triangle. For a triangle, the area is half into base. Base is V. Height is Q. Half into base into height. So half into V into Q. Half QV is energy stored. And the question, previous question here is this. You know, this angle is 30. This angle is 60. This is A. This is B. And they were asking you to find the capacitance, ratio of capacitances. How do you find ratio of capacitances? Capacitance of A. How can you find capacitance of A? Capacitance is given by what? Slope of the graph. That means tan theta A. That is tan 30. Why 30? Look at the angle that A is making. A is making 30 degree. Tan 30 is 1 by root 3. Right. Similarly, what is CB? Capacitance of B is what? Look at this. B. It is tan theta B. It is tan 60 because it's making an angle of 60 here. It is root 3. So what is CA over CB? The ratio is 1 by root 3 by root 3. Root 3 goes to denominator. So 1:3. Did you understand? Now, this is an important concept. We have done this many times. Anyway, I am doing it one more time. There are 8 cases. Case number 1, slab introduced. Slab introduced. Battery connected. Battery connected. It's like a shortcut, and they'll give it like different cases in school, but this is the best way to do this. Slab introduced, battery connected. Slab introduced, battery disconnected. Slab taken out, battery connected. Slab taken out, battery disconnected. Slab introduced, you have a capacitor, okay, and then it is connected to a battery, and you are introducing a slab inside. Okay, it doesn't matter whether it is conducting slab or dielectric slab. Okay, whatever it is, number 1, capacitance increases. Look at this. I'll repeat. You know what is the first case? Slab inserted, battery connected. You just have to know 2 things. One is, if the battery is connected, voltage is constant. Potential difference is constant. Battery is still connected. Voltage is constant. Constant supply voltage is still there. So, first one. What about, okay, battery disconnected case? What about battery disconnected? There is nobody to give further charges. So, charge remains constant in such cases. I'm repeating. Yes, Hannah. Right. Okay, I'm repeating. There are 2 cases. You have to keep in memory. Right. First one is what? Battery connected and battery disconnected. Those are the cases. Battery connected, battery disconnected. Repeat after me, please. Battery connected, voltage is constant. Battery disconnected, charge is constant. If battery is, that's common sense. Battery is disconnected means there is no agency that can give charges. Which means what? Whatever is stored in it will be a constant. Charge will be a constant. Okay, so there are 2 aspects. Number 1, battery connected. That means voltage is a constant. Battery disconnected. That means charge is a constant. See this now? First one. Tell me, what happens when slab is introduced? When a slab is introduced, you know, capacitance will increase for sure. Because capacitance is epsilon 0 A by D usually. But when you introduce a slab, it becomes D minus T. What happened to denominator? It decreased. So automatically capacitance increases. Okay. So whatever be the nature of the slab that you're introducing, when you introduce a slab, capacitance increases for sure. So when you take it out, capacitance decreases. See, when you introduce a slab, if capacitance increases, when you take it out, capacitance decreases. That's common sense. When you put the slab in, capacitance goes on increasing. Then when you take it out, capacitance should decrease. Keep that in mind anyway. So slab introduced, battery connected. Battery connected means what? I told you voltage will be a constant. Voltage is a constant. Now the third point, C and V are there, no? How do you write Q now? Q is equal to CV, right? V is a constant. V is a constant. What is happening to C? C is increasing. So V is a constant, but C is increasing. So charge is also increasing. Fourth one, energy. Energy equation is what? We had 3 equations for energy. Half CV square, Q square by 2C or half QV. And you must choose the equation judiciously. You must choose the equation containing constant quantity. Who is constant here? V is constant. So you must choose either this one or this one. I'm going with this one. Last one is also fine. Okay. Half CV square. Tell me what's happening to this. V is a constant here. Half is a constant here. What's happening to C? C is increasing. So energy also increases. Right. So that is how I write it. Did you understand this? Okay. Next one. Slab introduced, battery disconnected. Right. Battery disconnected or removed. Battery disconnected. Okay. Slab introduced or battery disconnected. Slab introduced or battery disconnected. Tell me what you're going to do. Slab introduced, battery disconnected. Tell me what. Number one, capacitance increases. Why? Because slab is introduced. When slab is introduced, capacitance should increase, right? And then battery disconnected. I told you, if battery is disconnected, there is no further flow of charges. So charge will be a constant. Charge will stay constant. Third point, C and Q are written. So V will be what? V is equal to Q by C. Q is a constant. C is increasing. Denominator is increasing means voltage is decreasing. Look at that. Look at that. And the fourth one, energy. I must choose which equation for energy? An equation that contains Q, constant quantity. So I can choose this equation. Q square by 2C. Q square by 2C. Tell me what happens now. Q is a constant, so numerator is constant. 2 is a constant. What happens to C? C is increasing. So energy must decrease. Understood? So we are writing the third case here, slab removed and battery connected. Slab removed means what? Capacitance decreases. Because when you insert the slab, if capacitance increases, when you take the slab out, capacitance decreases. Then voltage. What about voltage? Voltage is a constant because battery remains connected. Then charge is what? Charge is CV. Right. C is what? C is decreasing. V is constant. So this is decreasing. Energy. Which equation should I choose? I should choose an equation with constant quantity. So I can go with this one. Half CV square. Tell me what now? V is a constant, but C is decreasing. C is decreasing means energy is decreasing. Understood? Fourth one, slab removed. For practice, you can type this also. Slab removed, battery disconnected. But never ever learn this by heart. It's so easy. Right. Slab removed, battery disconnected. Fourth case. Slab removed, battery disconnected. What happens now? First case. Slab removed means capacitance decreases. Because when you insert the slab, if capacitance increases, when you take it out, capacitance decreases. Right. Number two. Battery disconnected. Battery disconnected means charge is a constant. There is no further flow of charges. Then third one. V is what? V is equal to Q over C. Look at that. Q is a constant here, but C is decreasing. Denominator is decreasing. So this value must increase. Then fourth one, energy. Which equation should I choose here for energy? An equation with Q in it. Q is the constant quantity. So Q square over 2C. Q is a constant here. 2 is a constant here. C is decreasing. So denominator is decreasing means energy must increase. Solve the four cases. There are four more. Then we'll do one question. Did you finish? Tell me when you finish this. Okay, thank you, Ichila. Maharshi. Right. Now these are the four cases, and then there are four more cases. But you can do it on your own. Now, next one, fifth case. Plates are moved apart. Plates are moved apart. Plates are moved apart. Battery connected. Plates are moved apart means what? You hold the plates using an insulating handle, right? And then they are moved apart like this. Okay, the capacitor plates, you're holding them using insulating hands. Why? Because otherwise charges will leak through your body. Understood? You should hold it using an insulator. Understood? Anyway, you're moving them apart. What happens now? Tell me, capacitance is epsilon 0 A by D, right? And what happens now? When you move the plates apart, distance is increasing. So denominator is increasing means capacitance decreases. Okay, so capacitance decreases. Now second point is battery connected. Battery connected means voltage is a constant. Right. Third one. Right. Q is equal to CV. It's like a shortcut. If you learn this, it's very easy. These kind of questions, no? Q is equal to CV. V is a constant, but C is decreasing. So energy, charge is decreasing. Fourth one, energy. Which equation should I choose? An equation with V in it. So I go for half CV square. Half CV square. What's happening to half CV square? Half is a constant. V is a constant, but C is decreasing. So decreases. Energy decreases. Hope you understood this. Right. Aishi, is that clear? Aishi, Kushi, Lavanya, Hemasri. Okay. Right. All right. Fine. Thank you. Right. Now the fourth case, sixth case, no? Sixth case. Plates are moved apart, battery disconnected. Battery disconnected. Okay? Plates are moved apart, battery disconnected. Try that yourself. Plates are moved apart means what? Write down this equation epsilon 0 A by D. Moved apart means the distance is increasing. Right. When the distance increases, denominator increases, capacitance decreases. Right. Number two, battery disconnected. Disconnected means no more charges. Q is a constant. Third one, V is equal to Q over C. Q is a constant. C is decreasing. Denominator is decreasing. So this value must increase. Fourth one, energy. Energy is what? I must choose this an equation with this quantity in it, right? Because Q is constant here, no? Q is this one I'll take. Q square over 2C. What's happening to Q? Q is constant. What about 2? 2 is constant. What's with C? C is decreasing. So denominator is decreasing means energy is increasing. Rest of the case I am giving as homework 7 and 8. Plates are moved towards. This is plates are moved apart. Now plates are moved towards each other. Plates are moved towards each other. Case number 7. Plates are moved towards each other. What happens? Distance will decrease. So denominator decreases. Capacitance increases. Plates are moved towards each other. Battery connected. Plates are. Case number 7 is homework for you. You can do that now. Nothing to be learned here, no? You will write it automatically. Plates are moved towards each other. Battery connected. That is case number 7. Plates are moved towards each other, battery connected. Plates are moved towards each other, battery disconnected. Plates are moved towards each other. This was moved apart, and here in this case, they are moved towards each other, opposite of it. Moved towards each other, battery connected. Moved towards each other, battery disconnected. Moved towards each other, battery disconnected. Read question number 10. In the circuit shown, capacitors are connected to a battery with the switch S closed. In the circuit shown, I will draw the figure. This is the circuit now. I have the circuit here, couple of batteries, couple of cells, and then what? We have a capacitor here. This is a capacitor, right? And there is another capacitor through a switch, right? Okay, another capacitor through a switch. Okay, this capacitor is C, this capacitor is C. They are identical, right? Identical capacitors. So if you've drawn the figure, just read this. In the circuit shown, capacitors are connected to a battery with the switch S closed. The switch is closed here. Now the switch is closed. See the switch? That switch is closed there. The switch is now opened. Now you are opening the switch. Case number 1, the switch is closed. Case number 2, you are opening the switch, and the space between the plates of capacitors is filled with a dielectric of dielectric constant 3. You are filling this with a dielectric of dielectric constant 3. You are filling this with a dielectric of dielectric constant 3. Understood? In case number 1, switch was closed, nothing was there inside. And in case number 2, you are opening the switch and you are filling the capacitors with a dielectric material. Find the ratio of total energy stored in both capacitors before and after the introduction of dielectric. So there are 2 cases. I'll illustrate a question. Case number 1, this is a setup. And then what? The switch is closed. You have to find the total energy. Then case number 2, you're opening it, you're filling these with the materials, and then finding the energy again. Find the ratio of those energies. I'll do this. If you don't understand, I can repeat. No issues. Just see what I'm doing. So in case number 1, I'm doing case number 1 first. Case 1. Okay. I need a lot of space. Right. Case number 1. Tell me, what about case number 1? These capacitors are in parallel. Would you agree? Look at that. Because this point and this point. Take these points. Where is the top plate connected? Top plate of this capacitor is connected to the point A, and bottom plate is connected to B. Look at that. And for this capacitor also, top plate is connected to the point A, and the bottom plate is connected to the point B. So both the capacitors are connected between same pair of terminals, A and B. Look at this. This capacitor is between A and B, and this capacitor is also between A and B. That means they are in parallel combination. So I can find the energy. What is the equation for energy? Energy stored can be written as half into Cp into V square. Half into Cp into V square. That is equal to half into C plus C into V square. That is half into 2C into V square. Right. Half into 2C into V square. Half into 2C into V square. Okay, let's keep it like this. Okay. And I'm keeping this as, you know, I take this half Cv square as U, or I call it Ui, initial configuration, no? Initial. So I can call it what? 2U. So Ui is equal to 2U. That is my initial energy. That is the initial energy for the first configuration, right? I'm repeating this. In case number 1, since both the capacitors are in parallel, I can find the energy using this. Energy in the initial configuration is half into Cp into V square. Right. Cp is what? Parallel combination of these two, and that would make it C plus C. C plus C is 2C, parallel combination 2C into V square. So half into 2C into V square. And then apart from 2, what I have is half CV square, which I will call U. So that makes it 2U. Now, this is first case. Case number 2 will have 2 parts. You know, case number 2, I open this and I'm filling this with the material, So what is the new capacitance? I'm writing the new capacitance now. Old capacitance was what? Old capacitance was, you know, old capacitance was epsilon 0 A by B. Now the new capacitance is epsilon 0 3A by D. Why? Old capacitance was with air, that was epsilon 0 A by D, but the new capacitance is with what? New capacitance is with epsilon 0, epsilon r. It's a material, no? Epsilon r A by D. Epsilon r is 3 in the question. They have given that it is 3. 3 epsilon 0 A by D. So if I take epsilon 0 A by D together, that's nothing but our old capacitance. So the new capacitance is 3 times C. Okay? New capacitance, just keep this in mind. New capacitance is 3 times C. So I'm finding case 2. I'm finding U1 final. U1 final. U1 final means what? Energy of first capacitor. Energy of first capacitor. I call it C1. I call it C2. C1 is equal to C. C2 is also equal to C. Energy of the first capacitor. What is that capacitor now? That capacitor is still connected to the battery. Still connected to the battery because this part is broken. That means that part is removed from the battery. While this is still connected to the battery. This is still connected to the battery. No? This circuit is intact. Am I correct? So I can take this as what? Still connected to battery. Case number 1. Case number 1. Case number 2. You know, capacitor 1 connected to battery. I would say that it is connected to battery. Even now it is connected to battery. Right. Capacitor 1. See this? Capacitor 1 is connected to battery even now. Right. The circuit is perfect. Nothing is broken there. So I can use what? Connected to battery means, you know, I should use which equation? Connected to battery means voltage is a constant. So I must use half into 3C into V square. Why should I use this equation? Because connected to battery means battery remains connected means voltage is a constant. So I must use an equation with voltage in it. So half into 3C into V square. Why did I use 3C? Because the new capacitance is 3C. So it's like half into C into V square. And what is this? I called half CV square by the name U here. So that makes it 3U. So I got U1 final. U1 final I got now. That means final energy of first capacitor. I got it. Okay. So this is first part. Now, what does second capacitor? Capacitor 2. I can do capacitor 2. Tell me what? Capacitor 2, battery removed. Look at that. For that capacitor, battery is removed now. Battery is disconnected. Why? You see a break here, no? That means that capacitor is out of circuit now. That is removed from the circuit now. Battery removed. Battery removed. So how do you find U2F? For that capacitor, battery is removed. Battery is removed means there is no flow of charges now, which means charge is a constant. So I'm using this equation, Q square by 2 into 3C. Why did I use 3C here? Because the new capacitance is 3C. So Q square by 2 into 3C. Why should I choose this equation itself? Because second capacitor is battery removed case. Battery removed means Charge is a constant. Charge is a constant. So I must use an equation with charge in it. What is q square by 2c? Q square by 2c is same as half cv square, which I called by the name u. So that makes it u by 3. U by 3. So u to f I got. U to f also I got. Okay, u1f I got here. U2f I got here. So I can find u final now. U final is these two added. U1f plus u2f. Okay, that makes it 3u plus u by 3. That is 3 comes here, 9u plus u. That is 10u by 3. 10u by 3, u final. This is u final. Equation number 2. And they are asking you to find out the ratio of initial energy to final energy. What is ui by uf now? Ui was 2u and uf is 10u by 3. Then u and u are cut. This goes to numerator, 3 into 2, 6 by 10, which is 3 by 5. Understood? And if you want to check if your answer is correct or not, there is a shortcut which is used in entrance examinations, competitive examinations. It's a previous IIT question, it's a previous board question as well. But for boards, you can't write the shortcut. I'll tell you the shortcut. Ui to uf is 2k divided by k square plus 1. You can use it to check if your answer is correct or not. K value is what? Dielectric constant is 3 in the question. So 2 into 3, 6 by 3 square, 9. 9 plus 1, 10. 6 by 10 is 3 by 5. For entrance examination, you can get the answer in less than 5 seconds. But for boards, you have to show all these steps. Did you understand this? See this? The question is this. We have two capacitors connected like this, and then they are connected to a cell. Initially, the switch is on, and the question is to find the ratio of energy now. And in second case is what? You are breaking this. You are switching that circuit off and then filling these with material of dielectric constant 3. And then what? Tell me what initial energy I can find using this. It's a parallel combination of capacitors. Why? The top plate is connected to A, top plate is connected to A. Bottom plate is connected to B, bottom plate is connected to B. So they are in parallel combination. So for parallel combination, the equation is half into Cp into V square. Parallel combination is C plus C, C1 plus C2. So half into C plus C into V square. So half into 2C into V square. Half CV square together would be called U. So that makes it 2U. I call the initial energy as 2U. In second case, when you break this, there are two cases. This capacitor is still connected to the battery, while second capacitor is removed from the battery. It is broken here. The circuit is broken there. Okay. Right. And then it is broken there. And then what? You're finding the new capacitance. C was epsilon 0 A by D. When you fill it with material, epsilon 0, 3 into A by D. That is 3 times epsilon 0 A by D is C. So 3C. The new capacitance is 3C. Keep that in mind. And taking this capacitor and finding the energy. It is still connected to battery. Connected to battery. Connected to battery means voltage is constant. So you must choose an equation with voltage in it. Half into 3C into V square. Why did I choose 3C? Because the new capacitance is 3C. So apart from half CV square, what we have is 3. Half CV square is U. So 3U. For the second capacitance, it is broken from the circuit, is removed from the circuit. And then what? In that case, U2F. I told you that is removed case. Battery removed means what? Charge is constant. If charge is constant, I must use an equation with the charge. Q square by 2C. But in place of C, it is 3C. So Q square by 2C can be taken together. It is U by 3. Having obtained U1F and U2F, I must add them up. The final energy. Initial energy was 2U. Final energy is 10U by 3. Take the ratio UI by UF. That is 6 by 10 or 3 by 5. And the shortcut is UI by UF is 2K by K square plus 1. K value is 3 in the question. So 2 into 3, 6 by 3 square plus 1, 10. 6 by 10 is 3 by 5. And right. Find the effective capacitance. Find the effective capacitance. Find the effective capacitance. Find the effective capacitance for the combination shown. Find the effective capacitance for the combination shown. Find the effective capacitance for the combination shown. Find the effective capacitance. It's a stair-like structure. Stair-like structure. Find the effective capacitance for the combination shown. Draw the figure. Tell me when you finish. Find the effective capacitance between A and B. Right. Effective capacitance for the combination. Tell me when you're done with writing. Okay, thank you. Right, Angela. Right. So how many capacitors do we have? 3 capacitors. 1, 2, 3. So I'll just draw one plate here. Look at that. I'll just draw one plate here. This is one plate, no? This is second capacitor, right? One plate here. This is third capacitor, right? One plate here. Draw the figure if you want, right? And here it is, one big plate like this, right? So I'll take one by one. What about this capacitor? This is also B because it's like a square plate. Now one plate is square. It is understood. They won't give you, but it is understood. It is one square plate there. Okay. So what is the capacitance of the top part? This is C1, one capacitor, C2, second capacitor, C3, third capacitor. Okay. I'll write down the first one. C1 is equal to epsilon 0, A. What is area? Area is B square divided by D. Did you understand? I'm taking 3 capacitors here, C1, C2, C3. Look at this. C1 is the first capacitor. Epsilon 0, A by D. What is area of this plate? Area of this plate. One side is B, the other side is also B. It is a square, so area will be side into side. That is B square. This is actually area is equal to side into side. That is B square. Look at this. That this is how it looks like if you look at the front view. This side is B, this side is B. Understood? So it's like this. See this? It's like this. It's like this. Okay, this side is B and this side is B. See this? B and B. B square. Understood? B square by distance is D. What about second capacitance? C2 is equal to epsilon 0. There also the area is what? This side is B, this side is B. So area is B square by, what is the distance? This side is D. This distance is your forgot to give this distance. It is D. So this is D. Altogether D plus D. That is epsilon 0 B square by 2D. Correct? And for the third one, tell me what capacitance is. C3 is equal to epsilon 0. There also the area is what? This side is B. This side is also B. So epsilon 0 B square by D plus this distance is D. This distance is D. This distance is D. So D plus D plus D. So epsilon 0 B square by 3D. Now these are in what? These are in parallel combination, top, bottom. Okay, top, bottom, it is parallel combination. So C1, 2, 3 will be C1 plus C2 plus C3. Tell me, then epsilon 0 B square is common to all. By D is also common to all, right? Epsilon 0 B square by D, only 1 remains. Epsilon 0 B square by D, 1 by 2 remains. Epsilon 0 B square by D, 1 by 3 remains. So it is what? 1 plus 1 by 2 plus 1 by 3. 6 is the LCM. This is 6 plus 3, 9 plus 2, 11. 11 by 3. So the final answer is 11 by 3 epsilon 0 B square by D. Understood?